Hi everyone, welcome back to another lecture of COP-3402. Today we're going to be looking at how we can create processes from within our C code by using the fork and exec syscalls. So as a recap, the way processes are created on Unix systems is sort of like cell mitosis, cell duplication. We use the syscall fork to duplicate an existing process. This creates a child process that is an exact copy of the parent at the point at which fork was called. And then we use the syscall exec to replace a process's instructions with that of a different program's. So it's important to note here that only fork creates a new process. Exec does not create a new process. Exec only replaces the instructions that a current process is running with that of a different program's, and then resets that program's program counter to 0 so that it can start from the beginning. And how do we create processes? Well, the flow is to usually use fork to duplicate a process. And what this will do is create, again, a copy of the parent process. And this includes copying the program's file descriptors, including standard I/O, as it says in this slide. So if I go over to my image here that I've taken, this is from the Linux programming interface. This is a nice slide, I think, that explains how process creation works. We have a program called A that's running, and we call fork. The memory of the parent A is going to be copied into the child here. And the child is going to be running at the exact point. It is a duplicate that will be running at the exact point at which fork was called in the parent process. And both of these processes may perform their own actions. A will eventually call the exec syscall so that it can run a different program instead. In this case, we're going to say B. And it will run until it's complete, then exit with some status code. The parent may use the wait syscall. We will not be using that in this lecture, but in future lectures and in the projects we'll be using this. The parent may use the wait syscall to wait for the child status to be updated, to be passed to the parent, and then the parent can continue executing as normal. And just to reiterate, the fork syscall will give the child a copy of all the parent's memory, including its file descriptors. So here we can see if there's a process that has some file descriptors open pointing to a file table before a call to fork. After a call to fork, the child will have the same file descriptors as the parent, and they will point to the same locations in the file table. And you can ignore this subfigure C here. That'll be useful for a future lecture when we go to close file descriptors. Let's go back to the slides. And if fork only duplicates a process, then the way that we actually ensure the child or enable the child to do something different is by using the syscall exec, as we saw in that figure previously. And here is just the summary of the man pages for fork. So when you call fork in your C code, it returns the PID of the child process to the parent, and to the child it always returns 0, and on failure it returns -1. And this is going to be a little weird to wrap your head around at first because we're essentially running two programs at once from one piece of source code. So I'm going to give you some examples now of how to use fork. So I'm in my terminal here. I'm going to run tmux so that I can split my screen and have my code that I'm running on the right and my code that I'm editing on the left. I'm going to run make clean in my current directory. I think I have a bunch of files here. Okay, so I'm going to run make now. Make all to compile all these files that I prepared for these examples. I'm going to open fork1 first, and let's go through this line by line. So we have our includes, and then in the main function we're calling fork. If I hold shift and press K, you can view the man pages in Vim for this syscall. And you'll see actually here that fork returns a PIDT type. Well, if I hold shift and press K on PIDT here, we can actually see the man pages for this. And it tells us that this is a type used for storing process IDs, process group IDs, and session IDs. It is a signed integer type. Okay, so all we're doing in this function is calling hello world. In this program, I should say, is calling hello world. So let's try running the fork1 program here. And we'll see that it prints hello world twice. And the reason for that is because after this call to fork, on the line in which my cursor is highlighting presently, the parent process will fork duplicate into a child process, and execution will resume from the exact point at which fork was called. So both the parent and the child are going to call hello world. So let's look at the next example here. bit more complex. In this example, we're declaring our PID type variable. We're going to use the sleep library call. I believe it's a library call. Let's check. man3 sleep. Yep, it's a library call, because it's in the section 3 of the manual pages. So section 2 is syscall, section 3 is library calls. So here we're calling sleep, waiting for 8 seconds. Then we're calling fork, storing the result in this PID variable. And then we're calling printf with hello world and sleeping for 8 more seconds. So really we're going to see the same thing as we saw before, but with some delays before and after the call to print. So let's try running this first. And I'm not going to do anything special here. I'm just going to wait for a few seconds for the call to print to come out. And note that we're not calling fork until right before the call to hello world. So now we've called hello world. We're going to wait 8 more seconds, and the program will then terminate. Okay. So now this time, let's try running this program in the background. So I'm going to run fork here, fork2, and while it's running, I'm going to press Control-Z to send it to the background. And now I'm going to type PS to view the running processes. You can see there's only one process here, 33316. But once hello world is printed, let's wait for it. It should be printed soon. Oh, it's in the back. I'm sorry. The process is suspended, so we can resume the process by running BG to run it in the background. And the sleep syscall had already passed, so I'm going to actually run this program again. This is actually good because I can show you a different way to run this. If we want to run a program immediately in the background, we can put ampersand at the end of the shell command. So this will run the call to fork2 immediately in the background. So it's running. I can type PS, and you can see there's only one process, 3332. But once we see the output hello world, if I run PS again, you can see a new process has been created with a different PID, 33340. So that's to show that forking does in fact create a new process. And now the process is done. So if I type PS, you can see the process is finished running. Let's see the next example, fork3. Oops, fork3 .c is what we want to look at. So here, we're going to be calling fork first, and then we're going to be doing different things depending on whether we are in the child or the parent. So first we're checking for -1 because fork returns -1 in error. So we're just checking for errors. This should look pretty familiar, the syntax of calling fork, or I'm sorry, calling p error, passing the name of the function that failed. Then if we have 0, well, 0 means we're in the child process, so we'll print out the message printf from the child. Otherwise, we'll print printf from the parent, and since fork returns the PID of the child if we are in the parent process, then we can print the value of that PID here. And there's different ways, different format specifiers you can use for the PID, some that are technically more correct, but since PID is under the hood a signed integer, we can get away with just using %d here. So I'm going to run this, and then I want to talk more about this example too, but first I want to run it. And you can see we have printf from the parent and printf from the child separately. And also, you'll notice that in the child process here, we're calling _exit. Now, this is a convention in Linux, Linux programming that is. When you are exiting from the child process, you should use _exit and not exit. And the reason for this is because exit without the underscore does some cleanup tasks and could trigger some functions that are registered with the exit command or with the exit of a process. And these should be left to the parent. The child should generally not be doing these cleanup tasks because it might interfere with tasks that the parent is going to do once the child is done running. So in general, you want to use _exit when you are exiting from a child process. So now let's look at the next example here, fork4.c. And this is actually the same as the previous example. The difference here is that we're using this more idiomatic variant of using the switch statement. So you'll see this pretty common in Linux programming code, especially in the examples in the LPI textbook. They'll be using switch statements and then cases. And we don't have to actually break here. I can remove that. Because in each of these cases, we're exiting the program early. So we don't need to have break statements between our case labels. So case -1, we have an error. Case 0, that means we're in the child, so we print out from the child. default that, well, if we're not -1, we're not 0. The only other option is that we're in the parent, and the PID must therefore store the ID of the child process. So if I run this, if I make it again, exec, actually before I run this, I want to show something else here. You can actually move this assignment to directly inside of the switch label here. Not always necessary, but I think it's cool to do. And we can run make here, make fork 4. That will compile the code for us, and then I can actually run that code. And you can see it had the same output as last time. And the order in which this appears, printf and parent and child, I think it just depends on how your operating system is scheduling these tasks. I don't think there's a way to really control it. All right, so now that we've reviewed fork, I want to take a look at exec. This is going to be different. We're not going to be using fork yet. First, we're going to be using just exec to replace processes with other processes, other program code, and then later we'll combine them. So for now, let's look at exec1.c. So this is a very, very basic call to exec. What we're doing here is storing a path name variable, storing the string getPID in the path name variable. We're making an array here of 2 strings. The first is getPID, and the second is the null string, null. And then we're calling execv. Now, what does execv do? Well, let's look at the man pages for exec. So I'm going to hold shift and press K here. And you can see there's actually a whole family of exec functions. They have different suffixes. They all start with exec, but they have different suffixes, or suffices. I'm not sure what the plural of that word is. There's execl, execlp, execle, execv, execvp, and execvpe. This one's actually, you have to use a special macro here to access execvpe. Let's walk through these one at a time in these examples and see how they're all different. So the first one we're going to look at is execv. Now what execv does is let you pass in a argv variable and the name of a program you want to run. So first is the name of the program you want to run. And the second argument is the argv variable, which is an array of strings, which should first store the name of the program you are running, and then afterward is all the command line arguments to that program. Now we have no command line arguments to this getPID program, so we're just going to pass null to signify the end of the argv. And this is what you have to do. You have to specify null at the end of the list of arguments for execv to work, or any of the exec functions to work. And what is this getPID program? Well, I'm going to open another window here at the bottom. It's just a small C program I wrote. Let's see if I can open it up, getPID.c. All this does is use the getPID syscall, I believe it's a syscall, yeah, section 2, and it returns the ID of the currently running process, or the calling process. So all this program should do, if we run it, is just print the ID of the currently running process. So we're going to call execve, replace this program's memory, or instructions with those of the getPID program, and we're going to pass its arguments as argv, which by convention will just be the name getPID and then null, and to signify the end of arguments. And since execv replaces the currently running programs, the processes, instructions with that of a new program, we should never reach the following lines of code, because the program should only continue running as the new program we're calling, getPID. So if anything else happens, it must be an error, so we can repeat error, and then we should actually return 1 to signify an error. So I'm going to run make here on exec1, and now we'll actually run this to see what happens. Exec1. You can see it actually prints the PID of our process, 33638. I'm going to close that window, move on to the next example, fork2.c. Oops, I'm sorry, exec2.c. Okay, so what if we wanted to run a process that's from our root directory, that's one of our programs like ls, so I'll do this on the right-hand side here, ls, or echo, or pwd, which we expect to be available to us from our path. We don't have to type the full path into these programs because we have them stored in our path variable. Well, if we use execv, we have to actually specify the entire path to this binary, which is going to be user van ls for the ls program, for instance. So if I run this, you can see it actually runs ls and prints out all the contents of my current directory. But this is kind of annoying, right? To have to specify the full path to ls whenever we want to run it. So instead what we can do is run, let's edit exec3.c and see something better that we can do. We can use the exec vp syscall instead. And what does the P stand for? The P stands for path. This means that our process will inherit the calling process's path, or that the, that the call to exec will first look up the program we're trying to run in the calling environment's path. So again, if I use printenv to print the value of my path variable, you can see user bin right here, user bin. I can highlight it better. Where is it? User bin, right here. User bin is on my path, so if I make a call to a program called like ls, my shell will actually look in the path variable, in all these directories in the path variable, until it finds a program called ls in one of these directories. And in this case, it finds it in user bin, and then we'll run that program and stop looking for programs to run. So the exec vp syscall here will actually let the calling process look through that path variable before it calls, look for that path variable for the name of the program we're passing to exec. So I'm going to run this again. So I'm going to say, actually I'll change this return value to be 1 as well. So I'll run make all, and I'll run exec3, and now we can see it also works and still prints the contents of our directory, so ls worked successfully. Now if we wanted to, we could actually pass arguments here, so I'll go over here to give this as an example. If I pass the -l flag, that is the flag for, maybe one flag, that's the flag for one listing per line. So if I run this, so if I run make all again and then run exec3, you can see we actually have successfully passed the L flag to ls from within our C code. So let's take a look at exec4 now. And here we're going to look at something a bit more complex, but I think it's worth showing. It's the last two suffixes that we have not seen yet. So here we're calling exec le. What does le mean? Well, the L in LE, I don't remember what it stands for, but it essentially means you can pass the arguments, the arguments to the program you're running as arguments to the syscall directly. So instead of having a separate array like we had before for passing here, so if I actually go back to the other file, you can see we passed this argv array in here. I'll exit exec4 again. .c. We don't have the argv array anymore. We're passing the values of argv directly into this call to exec le. And then we have to end it with null, like before. And because we're not using the p suffix, we have to specify the whole path to the program we want to run. And I want to run the printenv command. So remember, the printenv command, I just used it earlier, prints the value of an environment variable. Well, that's what the E in exec le stands for. We can pass a environment to our program when we run it, to our call to exec. So if I actually look at the man pages here for exec le and vp, we can actually see it tells us exec vp, let's see here. Well, it doesn't specify this clearly in this documentation, I think, but you can go in the GNU manual online and find a better demonstration of better explanation of how NVP works. So basically, we're passing a new environment, or I think it's an additional environment, it might be a new environment, to our, actually I think it's a new environment, to our program to run with after the call to exec le. So here we're saying, run with the environment where the value course code, the environment variable course code, is equal to COP-3402. And this is like the syntax for assigning values to environment variables. Name, =, value. So if I were to run this in my shell currently, course code, we get nothing because the course code shell value has not been assigned. But if I were to, let me increment this, if I were to run exec4 here, what will happen is, at this point in the program, we will replace this calling process's instructions with that of the printenv program, and we will be calling printdnv with the course code argument, and we'll be using this under the environment that's specified in this array here, where course code is equal to COP-3402. So what happens if we run this is that we get the result COP-3402 because we're printing the value of course code, which, if we correctly set it in the environment, which it seems we did, should be equal to COP-3402. Okay, so that's so much for exec. Now for the fun part, we're going to be combining them and running fork and exec in tandem, or one after another. So I have two examples of this, fork exec .c. I'm sorry, not fork exec .c. Fork exec 1.c. I have two examples. So the first thing we're doing here, setting up our headers, then we're getting this PID, we're making that call to fork to store it in this PID variable. We're going to exit in case of -1, because -1 means we failed. And let me make this a little bit smaller. If we're in the child, so 0 means we are in the child process, then what we'll do is print out a message inside the child process. We're going to set the program that we want to run to ls. We'll make a new argv variable here, where the first argument is null. I don't know why we're specifying the first argument is null. That should actually be, if I'm not mistaken, that should be instead /user bin ls, because the convention is to pass the name of the program you are running as the first argument to argv. And we're going to list the contents of the current directory, and then we specify null at the end of the list of arguments here. Then in the new environment, we just have null, so we're not changing the environment. We're actually giving this an empty environment is what we're doing. And if this works, then the execution should stop immediately. If it fails, then execution will continue. So if execution has continued, we must have had an error. So we'll print p-error, exec ve, and then use _exit to exit with a failure status code. And remember, in the child process, we use _exit. We don't use regular exit, because regular exit performs some cleanup tasks and may perform cleanup tasks, and also may call handlers that handle the exit function, like add exit or on exit, that we don't want the child to do, because that might step on the toes of the parent process. So the parent, if it's not a -1, if PID is not a -1 and PID is not 0, then it must be a PID, it must be something else, so that means we're in the parent process, and PID must store the value of the child's PID. So what we'll do is just print that the parent is still running, and then exit with exit success. So let's try making this code, because I made some changes to it, and then we'll run fork exec 1. You can see it says the parent is still running, it gives the child's PID, and inside the child process we can see we actually ran ls and printed the contents of the current directory. So one use of this that the LPI book mentions is setting up a server that accepts incoming requests and then calls fork and exec to create child processes that handle those incoming requests without terminating the server. Now let's look at one last example, fork exec 2.c. And in this one, we're doing basically what we've done before, declaring PID, assigning it to fork, exiting on error, printing that we're inside the child process, but now we're going to run sleep in the child process and sleep in the parent process. And we'll sleep for 10 seconds. Now let's try running this. Fork. I think did I make any changes? Let's see. No, I didn't. Okay, so, or yes, I did. It seems I did. Okay, so fork exec 2. So you can see inside the child process, I'll press Control-Z, and we can actually use to stop the process. CPS, just to verify, the child PID according to our code is 33921, and what do you know? According to the output of PS, that seems to be correct, because the child process was replaced with the program sleep, because we used exec VE here to replace it with sleep. The parent process is still running. They're both suspended. So what I'm going to do now is bring these programs to the foreground, and when I do that with FG, the child process, I expect it to end immediately because sleep continues waiting for time to pass even when it's stopped. So let's just type FG and see what happens. Yeah, you can see the sleep process was already done because 10 seconds had elapsed while I was talking after I had paused it. Okay, so I hope that was pretty illuminating, pretty useful. I gave a ton of examples of fork and exec. This will be very useful for the assignments coming up. We'll also have to go over wait eventually, but I think this is the bulk of how fork and exec work. So if you can get this, you can, I think, grapple with the rest of this course pretty easily. The rest of the stuff related to fork and exec, that is. All right, so I'm going to call it there. Have a good day, and I hope to see you all in lecture soon.